In this video, we're gonna finish chapter 19. Remember, we won't talk about 19.4. So 19.3 is the last chapter we're gonna talk about. Before we do that, I want to give the answer to the problem in the previous lecture. So in this problem, we try to pick a suitable indicator for these two types of acid and base titration. For the acid-base titration curve on the left, it represents a titration between a weak acid and a strong base by adding the strong base into the weak acid. Based on what we learned from the previous lecture, we know that once we start to add a strong base, we are creating a buffer due to the existence of these common ions. So you can see the pH change during this region is not very rapid with the addition of the strong base. However, when it's near the equivalence point, the change of pH is very rapid with the addition of NaOH. Then we have to look at the pH range that this indicator changes colors. So for methyl red, we can see the color change happens in this buffered region, right? So if we choose methyl red, it won't give us a very good indication result because it's gonna take a fairly large amount of the base to change the color of the indicator. However, if we pick a phenolphthalein, you can see the pH region covers the equivalence point. So in this case, phenolphthalein is a good indicator. For the figure on the right, it is the acid-base titration curve between a weak base and a strong acid. So it is the opposite of the figure on the left. In this case, we are adding the strong acid into the weak base, so the buffer region is at the beginning, and the range of pH covers the pH change for phenolphthalein. So for the same reason, because the addition of acid, right, the addition of the acid doesn't change the pH rapidly, so phenolphthalein will not be a good indicator for this titration. But for methyl red, because it covers the equivalence point, and the change of color will happen in this region. So we say methyl red is a good choice. Right, so I hope you get the right answer. The last topic we're going to talk about in chapter 19 is the equilibria of slightly soluble ionic compounds. The slightly soluble ionic compounds are the ones that we mentioned that insoluble, or we called insoluble in the previous chapters. But actually, no compound is absolutely insoluble. So they're slightly soluble, and the solubility is very low, so we can refer to them as insoluble. In this chapter, we're gonna see how to calculate the solubility or calculating the solubility constant for these ionic compounds. When we put a barely soluble ionic compound into water, most of the compound will remain as a solid. A very small portion of that solid can be dissolved in water. And for that very small soluble portion of the solid, because it's an ionic compound, we can assume it completely dissolved. So in this example, we have lead fluoride, which is a barely soluble compound, right? Because it's made of a metal and a non-metal, so it's an ionic compound. So for that small portion that is soluble, it will generate the metal cation and the anion. Remember, we have two fluoride here, right? So you're generating two fluorides. The reaction quotient for this reaction can be written as 0, notice you have the square for fluoride because the coefficient of 2. In this expression, because the denominator is a solid, right? So this is a solid, which means the reactivity is equal to 1. So we can rewrite this equation by moving the 1 to the left-hand side, right? So on the left-hand side, you have QC times 1, and on the right-hand side, you have the concentration terms on the numerator. And for this, the concentration terms, which indicates the product, right? So we say it's equal to QSP. So this is a reaction quotient regarding a solubility products. So these are the solubility products. So we have a SP as the subscript. This QSP could be greater, smaller, or equal to KSP. So KSP is the equilibrium constant for this solubility product process. Right? So when this QSP is equal to KSP, we said this dissolution of this ionic compound is at equilibrium, and that also means the solution has reached saturation. Saturation here means that the amount of this solubility products in the solution have reached the maximum concentration, which also means that no matter how much more solid you add into this solution, which is already at this equilibrium or which is already saturated, no more lead cation or fluoride will be produced from the dissolution of the solid because it's already saturated. Right, so here the Kp means is the solubility product constant, which also means the equilibrium constant when this dissolution of this ionic compound reaches saturation. For this lead fluoride, its solubility constant is equal to 3.6 times 10 to the negative 8. As you can see, it's a very small number. And so because KSP equal to QSP when it's at saturation, so we say this KSP value is equal to the lead concentration times the fluoride concentration square. So in general, when we have a slightly insoluble ionic compound with a general expression as MpSQ, so M means the metal and X is the nonmetal, P and the Q are their numbers in each formula unit. So when this ionic compound dissolved, it generates the metal cation with a charge of positive N and the anion with a charge of negative Z. So we can express the QSP or the KSP when it's at equilibrium as this equation. Okay, so basically, if we have this barely soluble ionic compound, and so it will generate the metal cation. The number is equal to P, right? Because here indicate the numbers with a charge of N plus, right? Also, the anion with a number of Q, right? So there's a anion with a charge of Z minus, right? So the QSP or the KSP when they're equal at equilibrium, right? So that will equal to the concentration of the metal cation, right? And the exponent will be the number or the coefficients in the equation times the concentration of the anions to the exponent of its coefficient in the equation. So let's look at a few examples. So for magnesium carbonate, so magnesium 2 plus, right? So carbonate is 2 minus. So when it dissolves, it generates the magnesium 2 plus and the carbonate, right, which is 2 minus. So for the solubility constant KSP is equal to magnesium 2 plus concentration times the carbonate concentration. In this case, because the coefficients for both of them are equal to 1, so we can ignore the coefficient here. So for the second reaction, when we have iron 2 hydroxide, right, so when it dissolve, it will generate 1 iron 2 cation and 2 hydroxide. So for the solubility constant for this equation is equal to iron 2 concentration multiply the hydroxide concentration square. Right? The square comes from the coefficient. And for this calcium phosphate, when it dissolves, it gives you 3 calcium cation and 2 phosphate. So for its KSP value, it's going to be the concentration of calcium to the third times the concentration of phosphate square. This table gives you an idea about the scale of solubility constant for some common slightly soluble ionic compounds. So earlier, our example is this lead 2 fluoride. Right, so compared to the other compounds in this table, it is more soluble, right, compared to the other solids. And we'll talk about how to compare their solubility using the KSP value in the later slides. When we put a slightly soluble ionic compound into water and the solution has reached saturation, we can say the system has reached equilibrium, or this dissolution reaction has reached equilibrium. At this equilibrium condition, we can actually calculate the equilibrium constant based on the amount of the salt that has been dissolved. So let's take a look at this example problem. In this problem, we have lead 2 fluoride again. So we add it into water and shake it to let it dissolve. So we find out for every 1 liter of this solution, there are 0.64 grams of this solid dissolved. And then we want to calculate the KSP, or the solubility constant, for this ionic compound. So first, let's list out the equation. We have the ionic compound dissolved into the metal cation and the anions. To calculate KSP, we need to know the concentration for both lead 2 plus and fluoride. So where does this cationized anion come from? It comes from the dissolution of the soluble portion of this solid. So the question tells us that the solubility is found to be 0.06 gram per liter, meaning that for every 1 liter of this solution, about 0.64 gram can be dissolved. So that 0.64 gram refers to the mass for the soluble portion of the solid. So if 0.64 gram of this solid are dissolved in 1 liter, what's the concentration of the metal cation and the fluoride? Right, so now the question becomes easier, right? Because we have the balanced solution here, balanced reaction here with the correct coefficient. So if we know the concentration of one of the reactants or the products, we can calculate the concentration for the others based on the stoichiometry. So the first step, we're going to convert that gram per liter into molar concentration. So for lead 2 fluoride, its molar mass is 245.2. So we can convert the mass into a number of moles, right, by dividing the gram by the molar mass. So 0.64 gram per liter is equivalent to 2.6 times 10 to the negative 3 moles per liter or molar. So this is the starting concentration, or the concentration of the solids that are dissolved. So based on the stoichiometry, because it has a coefficient of 1, and the light also has a coefficient of 1, so the amount of the light generated, light 2 plus, right, so it's equal, right, to the reactant concentration, which is also 2.6 times 10 to the negative 3. For fluoride, because the coefficient is 2, right, so the concentration is double, so it's 2 times the 2 times 6 times 10 to the negative 3. Right, so this will be the concentration for the lead 2 plus, and this will be the concentration for the fluoride. So now we know the concentration for both, so we can plug those into this equation and then calculate the KSP value, which is 7 times 10 to the negative 8. And again, it has no unit, right, because for the equilibrium constant, it should be unitless. So now let's take a look at this number. So earlier from the previous slide, we said that the solubility constant for lead 2 fluoride is 3.6 times 10 to the negative 8. But from our calculation, it's almost double of that. So why there is a difference between the tabulated KSP and the KSP we calculated from the experiment? Well, the difference is due to a very important assumption that I haven't mentioned yet. So when an ionic compound dissolves in water, it not only generates the metal cation and the fluoride. In this case, another species generated is Pb fluorine plus. Right, so this is another possible species that exists in the solution, and it is the aqueous phase. So we didn't account the existence of this species in our calculation, but this species actually does exist. So that's why our calculation have a higher KSP value than the tabulated KSP value. So for the tabulated KSP value, it will only consider this reaction. We'll only consider this reaction here, without considering the other possible species in the solution. But in this problem, we found that for this 0.64 gram of solid that is dissolved, it actually not only include the solid that generating the lead 2 plus and the fluoride, but also including the species that we didn't consider. Right, so that's why we have a higher KSP value compared to the tabulated value. In general chemistry, when we're dealing with the solubility constant question, we won't consider this other complex species. We'll only consider the metal cation and the anion, non-metal anion. In this example problem, we are given the solubility constant and try to figure out the molar of solubility. Right, so this is the opposite direction of the previous example problem. So in this problem, we're looking at the dissolution of calcium hydroxide. For each mole of the calcium hydroxide solid, it will dissolve and generate 1 mole of calcium cation and 2 moles of hydroxide. So the KSP is equal to calcium concentration times the hydroxide concentration squared, which is equal to 6.5 times 10 to the negative 6. So now we can list the ICE table. Here we don't worry about the concentration of the solid because it's not shown in our expression for KSP, right? So we don't need to care about it. For the calcium and hydroxide, initially their concentration is equal to 0. And for the change of concentration, the amount increase for calcium is equal to the molar solubility of the calcium hydroxide, right? Because we assume that it completely dissolved. The stoichiometry suggests a 1-to-1 ratio, right, between the calcium and the solid. So we have a plus S. And for the hydroxide, because the coefficient is 2, we have a plus 2S. Here S represents the solubility, right? So the amount of the solid that is dissolved. So at equilibrium or at saturation, we have a calcium concentration equal to the solubility, or the molar solubility. And the hydroxide concentration is equal to 2 times the molar solubility. Right. By plugging in this S and 2S into this equation, right, we can calculate S. So S is equal to 1.2 times 10 to the negative 2 molar. Right, meaning that because molar is mole per liter, right? So meaning that if you put some calcium hydroxide solid into 1 liter of water, 1 point times 10 to the negative 2 moles of this solid will be dissolved. The remaining will remain as a solid. Again, in this example problem, we're assuming that the only possible dissolution product is the metal cation and the hydroxide. But actually, if you do the experiment, you're gonna find out the molar solubility is around 2 times 10 to the negative 2, which is higher than what we calculate. And again, that's because our assumption, right? Our assumption is only calcium cation and hydroxide anion are produced from the dissolution. But in this case, calcium OH plus is another possible species that is generated from the dissolution of this solid calcium hydroxide. But again, we ignore it, right? So that's because in general chemistry, we won't talk about the formation of this complex species. So we won't bother about its existence in this type of problem, right? So again, in this class, when we're dealing with the solubility of an ionic compound, we only consider the metal cation and the non-metal anion, or the hydroxides. We don't worry about the other species that is generated from the dissolution of the solid. Because the KSP value, or the solubility constant value, is an indication of the equilibrium constant, which is the extent of this dissolution process. So the magnitude of this KSP can be used to compare the solubility of these ionic compounds. But we need to be careful that when we compare this KSP value, we have to make sure that this ionic compounds, right, they have the same total number of ions in their formula. For example, for these first 3 compounds in this table, right, they have total number of 2 ions, 1 cation and 1 anion. The anion could be also a polyatomic anion, right? So we don't separate the polyatomic anion. So for these 3, right, so to compare their solubility, because they have the same number of ions, we can just compare their KSP value, right? So the higher the KSP value, the higher the solubility, right? So the higher the KSP value, the higher the solubility, because KSP is equal to the concentration in terms of the products, right? So if you have more cation and then anion generated, which is the product, right? So that means this compound is more soluble. And for the other 4 ionic compounds in this table, they all have a total of 3 ions in their formula, right? So, but it doesn't matter what is a 1:2 ratio or 2:1 ratio, meaning the ratio for cations and anions. We can still using this comparison to compare their solubility, right? So the higher the KSP value, the higher the solubility. The solubility constant for an ionic compound can be affected by several factors. As we learned from the previous chapter, because the solubility constant is also an equilibrium constant, right? So temperature definitely have an effect on this constant. And the effect is the same as we discussed the effect of temperature in chapter 18. So we won't talk about again in this chapter. Now let's take a look at the effect of a common ion on the solubility of the ionic compound. In chapter 18, we mentioned that the concentration of the reactant or the product, right, can affect the equilibrium position. So if we increase the concentration on one side, that will push the equilibrium position to the other side. Right, so in this example, we have lead chromate. Right, so chromate is a very toxic metal polyatomic anion. Right, so we also call it oxy anions. So in this compound, lead is 2+, and the chromate overall is 2-. Right, so in this case, chromium is has a charge of a 6+. Right, it's also called chromium 6. Chromium 6 is very toxic, right? So chromium 3 on the other hand is not toxic and actually a very important trace element that our human body needs. Right, so for this solid, right, we know it is barely soluble, right? So when you put it in a water, you can see most of the solid remain as this yellow powder or yellow precipitate. And the solubility constant for this compound is 2.3 times 10 to the negative 13, right? So it's a very small number. So now let's say the system has reached equilibrium, right? So the solution here is saturated in terms of the formation of these solubility products. So what happens when we add sodium chromate into this solution? Sodium chromate is a soluble salt because the cation is sodium, right? So all the sodium salts are soluble. So when this sodium chromate is added, it will completely dissolve into sodium cation and the chromate anion. Right, so that means you're increasing the concentration of the chromate anion in the solution. So you're increasing the concentration of this chromate. So as we know, if we increase the concentration of a product, right, so which is on the right hand side, that will push the equilibrium precision to the left, meaning that there will be more solid PbCrO4 or lead chromate generated. So as you can see in the second picture, right, so as you add more of this soluble sodium chromate, you're generating more solids, right? This more solid generated is due to the net reaction or due to the shift of this equilibrium, because the equilibrium position shift to the left, which means more solids are generated. So because we're keeping the temperature same in this experiment, which means the KSP is also the same. So when the concentration of this chromate increase, and we have to keep the KSP the same, right? So when this increase and this value has to remain the same, that means the concentration of the lead must be decreasing in the solution. So the solubility of this lead chromate is defined by the amount of lead in the solution. So because the lead concentration also decreases in the solution, we said the solubility also decreases. Right, so let's look at it again. Right, so at equilibrium, you have equal concentration of lead and chromate, and when we multiply them, equal to the KSP value. When you add the sodium chromate, that will increase the concentration of the chromate, which will shift the equilibrium to the left and generating more solid. Right, so that in that case, we want the K to be the same because temperature remains the same. So the concentration of the lead must decrease. So the solubility of lead chromate will also decrease. Now let's look at example problem on the effect of common ion on the solubility of a calcium hydroxide. So earlier when we look at this equation, we only have calcium hydroxide dissolving water. But in this problem, instead of dissolving in water, we dissolve in a solution that contains 0.1 molar of calcium nitrate. Right? Because nitrate salts are all soluble, right? So calcium nitrate are all soluble. So that means in the solution, it already exists 0.1 molar of this calcium cation. So we can list our ICE table here. Again, we don't care about the solids, right? Because it doesn't appear in the KSP expression. So for calcium, at the beginning, it already have 0.1 molar. And the change of this concentration will come from the dissolution of the calcium hydroxide. Right, so the change of concentration is plus S. So the equilibrium concentration is 0.1 plus S. We know this S is going to be very small compared to 0.1. Right, so in our calculation, we can actually assume this 0.1 plus S, right, is approximately equal to 0.1. And for the hydroxide, same deal, because the coefficient of 2, the change of concentration will be plus 2S, so that will be the equilibrium concentration. Because the KSP of calcium hydroxide is given, so we can plug in this equilibrium concentrations into this expression, right, by making the assumption that 0.1 plus S is approximately equal to 0.1. Right, so by doing this, we can calculate S, which is equal to 4 times 10 to the negative 3 molar. And we can justify our assumption, right, because this S value compared to 0.1 is 4%, right, so which is less than 5%. So we say our assumption is valid. Okay, it's a valid assumption. So in this case, right, when we have calcium hydroxide dissolved in 0.1 molar of calcium nitrate, right, so only 4.10 to the negative 3 molar of calcium, right, can be generated from the dissolution of the calcium hydroxide. Or we say the solubility, molar solubility of calcium hydroxide is equal to 4.0 times 10 to the negative 3. Right, so from the previous example problem, we did a calculation, right? We got 1.2. We got 1.2 times 10 to the negative 12. Right, so we got 1.2 times 10 to the negative 12 from the previous problem with calcium hydroxide only. Right, so with the existence of this 0.1 molar calcium nitrate, right, its molar solubility decreased to 4 times 10 to the negative 3. Right, so that's due to this common ion effect. The solubility of the ionic compound can also be affected by the pH. So the pH could be changed when we add strong acid or strong base into the solution. In this class, we're only looking at the effect of adding strong acid on the solubility, because when we add hydroxide or strong base into the solution, most of the metal will also precipitate with hydroxide, so we are creating a more complicated system that is not required for understanding in general chemistry. So in this class, and for the examples in this slide, we're only looking at the effect when we add the strong acid or increasing the proton concentration into the solution. Right, so increasing proton concentration also means decreasing the pH. Right, so we will see how the solubility is affected by decreasing the pH. Right, so the first reaction, we have calcium hydroxide. So for this for the ionic compounds containing hydroxide, we know that its solubility can definitely be affected by the pH, because the hydroxide is one of our solubility products. Right, because pH is the negative log of the proton concentration. Right, so pH is the negative log of the proton concentration. And then we know that proton concentration is also related to the hydroxide concentration. Right, so Kw divided by the proton concentration is equal to the hydroxide concentration. So if we decrease the pH, right, so if we decrease the pH, so this is minus here. So if we decrease the pH, that means the hydroxide concentration will also decrease, right? So decreasing pH meaning that increasing the proton concentration, so the hydroxide concentration will be decreasing. So when the hydroxide concentration decreases, right, that will shift the equilibrium to the right, meaning that more solids need to be dissolved. Right, so the net reaction points to the right. So because more solids are dissolved, that means the solubility will be increased. So in this first equation, right, so decreasing the pH, right, by adding the acid, meaning that a decrease in hydroxide concentration. So another way you can think of it is the acid will consume hydroxide, right? The proton will react with hydroxide and produce water, right? So that will decrease the amount of hydroxide in the solution. So the reaction is shifted to the right, so the solubility will also increase. So for the second example, when a metal bind to a conjugated base of a weak acid, right? So for this ionic compound contain this conjugated base of a weak acid, we said that its solubility is also affected by the pH. In this case, we have calcium carbonate. Carbonate is the conjugated base of the weak acid, carbonic acid. Right, so carbonic acid is formed when the carbon dioxide in the atmosphere is dissolved in water. It's a very unstable molecule, so it's called metastable. So a lot of times you see this star on the superscript, meaning that this compound is very unstable or metastable. Right, so when calcium carbonate dissolves, it generates this carbonate ion. This carbonate ion because it's the conjugated base of weak acid, right? So it will react with the acid added or the proton added, right? So in this solution, if it decreasing the pH by adding more proton, that will consume the carbonate concentration, right? So the carbonate concentration will decrease. So when this carbonate concentration decreases, the reaction will also shift to the right, so that will increase the solubility of the solid, right? So more calcium will be generated. So the first one and the second one, they have something in common, right? So water, the hydroxide you can consider as the conjugated base of water, right? Water is both weak acid and weak base, right? So we can say that if this ionic compound contains this conjugated base or the anion of a weak acid, right? So we can say it will be affected by the pH in a way that increasing the proton concentration or decreasing the pH will increase the solubility of the compound, right? So it's pretty easy to remember, right? So if you have a solid, you try to dissolve it, or you try to let it dissolve more, you add acid, right? So acid will dissolve more solid, right? So that's kind of like a common sense, or that's something we assume that would happen, right? So here in this example, we see why it happens, right? But for a compound that contains an anion from a strong acid, right? For example, like hydrochloric acid or hydrobromic acid, or even like a sulfate, which comes from the sulfuric acid, right? So these anions come from the strong acid, or they're the conjugated base of the strong acid. These anions do not interact with a proton, so no matter how you increase or decrease the pH, it won't affect the solubility of this type of ionic compounds. Right, so here we only talk about decreasing the pH, right? So again, if we add hydroxide, it becomes more complicated, and I won't test you anything about adding hydroxide or increasing the pH on the solubility. So now let's take a look at this example problem. So we have three equations. So I suggest you to pause the video and determine what's gonna happen if we add acid or add proton into this solution. So what happens to the solubility of each ionic compound? So for the first one, we have bromide in this compound, right? So bromide, it is a anion from a strong acid, right? Hydrobromic acid, right? So the equilibrium constant is not affected by the addition of the proton, so we said the solubility remains constant. So for the second example, because it contains hydroxide, right? So by adding the acid, we'll decreasing the hydroxide concentration. That will shift the equilibrium to the right, so the solubility will increase. For the last one, this sulfide is the conjugated base of hydrogen sulfide, which is a weak acid. Right, so for ionic compound containing this weak acid, increasing the proton concentration, meaning that it will consume this sulfide. Right? So this sulfide concentration will decrease. So the equilibrium position will be shifted to the right, and the solubility will also be increasing. So far, all the examples we have looked at are at equilibrium condition, or the solution is saturated. But there are also cases that we don't know whether it's saturated or not. Right? For example, if you try to make or produce some of this precipitate or the ionic compound by mixing two soluble solutions. So can we determine whether the solid is gonna produce or not? And the answer is yes, right? So we can compare the Q value with the K value. So we know that at equilibrium, QSP is equal to KSP, right? Meaning that the forward reaction rate is equal to the reverse reaction rate. So overall, there's no change. However, if you mixing some reactants and the Q value here is greater than the K value, right? So QSP is greater than the solubility constant. That means your system has a concentration of the solubility products that is above the saturated concentration or the highest allowed concentration. So in that case, there must be precipitate formed. Right? So those solubility products in etcher will form the precipitates until the concentration of the solubility products is equal to the saturated concentration or the maximum allowed concentration, right? Which depends on the solubility constant. When this QSP is smaller than the KSP, that means no precipitate will form because the solution has not reached saturation yet, right? So meaning the concentration of the solubility products are still lower than the highest allowed concentration, right? So it will only form the precipitate when it reaches that highest allowed concentration. So in this case, no precipitate will be produced. Right, so again, if Q is greater than K, precipitate will be produced. If Q is less than K, no precipitate will be produced. In this example problem, we're trying to determine whether this calcium fluoride will be formed or not. Right, so we are adding the calcium through the addition of calcium nitrate, which is a totally soluble ionic compound, and the fluoride comes from sodium fluoride, which is also totally soluble. And this is the amount and the concentration of each reactant. So basically, we mix these two solutions and try to determine whether this calcium fluoride can be formed or not. So the approach is comparing the QSP value with the KSP. So KSP is given here, so all we need to do is determine whether the QSP is greater or smaller than this KSP value. So the QSP for this equation equal to the calcium concentration times the fluoride concentration squared. So we need to know the calcium concentration and the fluoride concentration. And these two reactants are introduced right from these two solutions here. So we need to figure out their concentration, right? So when we mix them. So for calcium, right? So we add 0.1 liter of 0.3 molar of calcium solution. So the number of moles is equal to 0.03 mole. Some of you might say, why can't we just use 0.3 here directly? The answer is no, because the concentration changes when you mix it with this sodium fluoride solution, because the dilution, right? Because the volume is no longer the same. You have the same number of moles of calcium, but the volume changes, right? You have 0.1 liter of calcium solution, but you also mixed it with 0.2 liter of the other solution which doesn't contain calcium. So the calcium is actually being diluted when you mix them. So the concentration for calcium at the beginning after mixing is actually 0.1 molar. Right? So that's done by divide the number of moles by the total volume after mixing. So same for fluoride, right? So the number of moles is 0.012. By dividing the total volume, you get this 0.04 molar. Right? So this concentration is what you need to plug into this equation. Right? So by putting these numbers in there, we got a Q value equal to 1.6 times 10 to the negative 4, which is way higher than the solubility constant. So we know that when Q is greater than K, the solid will form, right? So this calcium fluoride will be a precipitate. So it will keep forming this solid until QSP, right, equal to the KSP value. And here you have a picture of this reaction, right? So you can see the solution become very cloudy, meaning the precipitate has been formed. There are a lot of natural processes or phenomena related to the solubility of ionic compounds, right? So you all have heard about the effect of ocean acidification on the stability of coral reefs, right? So here, thinking about what we just learned, right? So if we increase the emission of CO2 into the atmosphere, and we know the atmosphere CO2 can be dissolved in ocean, which will decrease the pH of the seawater. Right, so in the comment below, discuss, right, how does this increasing CO2 emission can affect the stability of coral reef. I'm pretty sure you know the answer, but in the comment I want you to explain how it impacts the stability of the coral reefs, right, based on what we learned in this chapter. So please do not turn off the video yet. So I'm gonna announce several important days as I sent out in the previous email, right? So the homework is due by March 31st, right? So these two problems is related to the content chapter 19.3, and these are the last two problems before the third midterm. Right? So the due date for homework is March 31st. By I think 23:59 p.m. right, so 1 minute before midnight. Right, so again, for your homework, you can use any scanning app. I told you guys about this free app called Genie Scan, right? So you can use in the batch mode and take pictures of your homework and turn them into one PDF file. So you can upload your homework on Moodle, right? So between chapter 19 and 20 on Moodle, there is a slot for homework 3 and also a slot for midterm 3, right? So make sure you upload the file in the right place. And for the third midterm, right, I'm gonna upload the exam on April the 1st. So April the 1st, I think that's Wednesday, right? So I will upload it in the early morning, and you can work whole day. So the due time is still 23:59. Right, so it's open book, right? So you can use internet or your textbook, right, on those questions. So it's gonna be a Word file, so you can either like work on it electronically, or if you prefer to print it out and work on it using a pen and then scan it, that's also fine. But make sure you scan everything properly and I can read your answer or your solution. Right, so it's also okay that if you want to get a blank paper and write down your solutions on there, that's also fine. Just make sure you scan every page in order. Right, so also upload it on Moodle, right, at the correct place. So for both homework and the midterm exam, I won't accept any late submission, right? So especially for the exam, right? So I will accept no late submission. And for the questions in the homework, I highly suggest you to ask me either by testing or FaceTime. All right, a lot of students have done so already. So I guarantee you that if you work on your homework and you know how to solve each problem, you're gonna do just fine in the exam. Right, so every day I'm available basically from 9 a.m. to 9 p.m. Right, just send me a message. So can we do FaceTime, or can I ask you this problem? I check my phone very frequently, so I can get back to you very quick. So if you email me, I might not check my email as frequent as I check my cell phone, right? So every day 9 a.m. to p.m. including the weekends, right? So if you have any questions regarding the homework, just contact me. All right, that's it.